All right, so today we're going to keep going with our free body diagrams. So this is, last time we did packet 1 of 3 or note session 1 of 3. I'm going to say this is the packet 2 of 3 that you'd want to keep if you think you're going to take college physics. And it's called Applying Free Body Diagrams. Before we get too far into it, go ahead and it says review. What does each variable stand for? What are the correct units? So go ahead and hit pause and try those out. So hopefully you had time to kind of look at our physics warm-up, the review, and I'm just going to go through it. Make sure you understand this part because as we go on, it's kind of like we're getting tougher with each problem we do. So what does each variable stand for? What are the correct units? Well, W, the way we're going to write it, is equal to weight, and the equation for weight, W equals mg. Weight is a force, so I'm just going to label here, weight is a force. And in physics class, forces are always measured in units of newtons. So you can see right there that weight is a force measured in newtons. Uppercase N stands for normal force. As soon as you see the force word there, units are going to be newtons. The one part that people always confuse, and it's just because it's kind of a new concept, it's a little confusing. When you see these coefficients, like mu sub s stands for the coefficient of static friction, that's just the number between 0 and 1. Since it's not a force, it's a coefficient, it has no units. Same for mu k, so coefficient of kinetic friction, no units, and coefficient of kinetic friction just means it's moving or sliding. All right, last part that's super important. Someone's going to say, well, Mr. Laurent, mu sub s is not a force. Well, how do you get it to become a force? That's a great question, because right there, mu s is just a coefficient. Fs is the force of static friction. As soon as you see the force word, that means it's measured in newtons. And then I'm just going to tell you, here's the equation that converts the coefficient, which is mu s. If you take that coefficient times the normal force, that converts it over so it becomes a static frictional force. Likewise, when you see F sub k, that's going to be for two objects sliding past each other. They'll experience a force of kinetic friction because of sliding. Again, because it's a force, the units are going to be newtons, and then your equation is very similar. So you're going to have Fk is equal to mu k times n. So take a second. Sorry, I got a little sloppy with the writing there, but make sure it kind of makes sense. And then we're going to go on to our next part, which is the 5 steps for success. Last time we looked in our notes at drawing free body diagrams, which are essentially taking a picture and turning it into a diagram where you put all the forces on an object. So now we're actually going to solve some problems. Last time it was all drawing, and then today we actually get a little bit of math and physics together, so it's good. So Kayla and myself have come up with, over the years, we've heard this presented different ways, but we've heard 4 steps for success. There's 7 steps for success. We've combined it into something we call the 5 steps for success. So whenever you have a forces problem, just always think you're always going to use the 5 steps for success. It's pretty catchy. So step number 1, it says draw a free body diagram labeling all forces. Each object will need an FBD. So this is actually what we did last time. So we talked about what a free body diagram does, but that's why we spent a long time actually making sure we can draw them, because you can see it's the first step in the 5 steps for success. So if we have an incorrect step and we mess up on number 1, then steps 2, 3, 4, and 5 they don't work. So step number 1, draw the FBD. Step 2 says pick a coordinate system based on which way the object, quote, wants to move. For most of our problems, the coordinates that we're going to use are going to be our traditional XY coordinates, where X is to the right and Y is up, as far as positive X is to the right and positive Y is up. When we get to ramps, and then if we get time to go to pulleys, then we're going to have to do what are called rotated coordinates, where the coordinates can actually move or kind of change position. But for most of our problems, just assume we're going to say positive X to the right, positive Y is up. Step number 3 for success, break vectors that aren't aligned with your coordinate system into their components using SOHCAHTOA. So that, we'll get more into it and it'll make more sense when we're actually doing a problem. But just know, if you're going to do SOHCAHTOA in physics, that means on your calculator you got to be in degree mode. But that's only if you want the right answers. All right, step 4, sum your forces in the X and Y directions. And then we get this Greek letter here, sigma, which means sum. So the way you say this is, this Greek letter means add up all your forces F in the X direction And then you'll do the same thing in your y direction. And that's step 4. Step 5, solve for what you're looking for using your kinematics equations and step 4 equations. And this is step 5. We're going to use the given want equation as well. So it's kind of interesting, but when we first started the year, we were only using the given want, what we call the physics format here. The physics format of fun. Now we have to do kind of 4 steps to set this up. So you'll see these problems are a little bit more involved, but if you can do these problems, it's basically saying you really know your physics from all the stuff we've done before. So let's try the 5 steps for success. Example number 1, it says calculate the normal force acting on a 25 kilogram box at rest on a table. So just kind of talking this through, you have a table. There's my table. And let's just draw a box there. And my FBD, I'm just going to put a dot for the point mass. And before I get too far, why don't you try doing the 5 steps for success and see how far you can get. And then when you're ready, come back and we'll see if we match up. All right, we're back. So hopefully you get a chance to try the 5 steps for success. Step for success number 1 says draw an accurate FBD. So we actually did this problem in our previous note session. It says calculate the normal force for a box at rest on a table. We did the FBD, I should say. So you should know that the force that always acts down is the weight. And then since it's on a table, there's a contact force there, or a force from the touch. And that force is the normal force. And remember that normal force always acts perpendicular to the surface of the table. So you can see there's a right angle right there. So our table, I know our table is not that green line. Our table is down here, but you can see that that normal force is perpendicular to where the table surface would be. All right, then you ask yourself, are there any other forces acting on this box? And I would say no. So I'm going to come over here and say we did step for success number 1. All right. Eventually we'll have them memorized. For right now we don't. So step for success number 2 says pick a coordinate system. And all we're going to do there is we're going to say this isn't a block that's on a ramp. It's not a pulley system. It seems pretty simple. So we're just going to go traditional. So I'm just going to say positive x is to the right, positive y is up, and then we put a check right there. All right. Step 3 says break vectors that aren't aligned with your coordinate system into their components using SOHCAHTOA. So I'm going to check my vectors. I'm looking at my normal force here. My normal force is going straight up. That is aligned with my y direction, so I do not have to do SOHCAHTOA on it. And then I'm going to check my other vector, w, going down, and that one is also in the y direction, but it's in the negative y direction. But again, it's along that axis. It's lined up with the y-axis, so I don't have to do SOHCAHTOA on that one either. So that's nice. No SOHCAHTOA on this one, but eventually SOHCAHTOA. Step 4 says sum your forces in the x and y directions. So let's come over here and we'll say we're going to add up our forces in the x direction. So to get your forces, you look at your FBD, and I'm going to say, are there any forces in the x direction? And the answer to that is nope. So there's no forces in the x direction. And then it says info from your FBD, we have no forces, but you do set it equal to MAX. So I'll say that's equal to MAX. Cool. And you're like, why would you ever do that? But it's basically telling you if your net force is 0 and you know the box has a mass, that means your box is not accelerating in the x direction. So even like a simple equation like that is actually pretty important. All right, so we did the x to be even Steven. We're going to go sum the forces in the y. And now we look and we got our normal force, and it's going up aligned with the positive y. So we're going to say that would be positive normal force going up minus w going down. And then in this case, it says the box is at rest. So we can set it equal to MAY. But we know since it's at rest, your acceleration is going to be 0. So what that really means is that MAY is equal to 0 because it's not moving. So that means that N minus W is equal to 0, which means that N is equal to W. And we know from before that W is equal to mg because that was our warm-up today. So there's an equation we came up with there. So notice we haven't plugged any numbers, and we came up with a nice little equation. So we have just completed step number 4 for success. Now, step number 5 says solve what you are looking for using your kinematics equations and the step number 4 equations. And use given want equation. Well, I didn't save much room for this because, in all honesty, it's not a bad problem. It's just more to show you the process. So given, we know in the problem statement they tell us the mass is 25 kilograms. We're going to assume that we're on Earth because they didn't say anything different. So you got the acceleration from gravity going down. And what are we looking for? We're looking for the normal force. Well, if you look at all of our old equations that we've talked about so far this year, we don't have a normal force equation. There's not an equation we came up with. This is the normal force equation is this. So we can't use a kinematics equation from before. So another tool we have, it says end. We can also look back at our step 4 equations. Well, the reason we go through this process is because in step 4 we actually came up with a nice little equation for the normal force. And the normal force is it's equal to mg, which in this case, m is 25 kilograms times 9.81 meters per second squared. So we plug, we chug, and we'll get 245.25 newtons. All right, so final answer, we're going to write in bright pink. Our normal force is going to be 245.25 newtons. And now notice I put the arrow above my normal force. Over here, it didn't have the arrow because I was just calculating the strength. So I got 245. When I put that arrow there, since force is a vector, you're going to have to include the direction that normal force is acting, which according to my picture, it's in the y direction. So if you remember back, I could say it's going up, or I could use our little system and say y hat. But that would be our final answer right there. Normal force, 245.25 newtons in the y hat direction.